I'm Zane from thecarbondoctor.com, and in today's whiteboard lecture we're going to discuss stoichiometry. It's a foundational topic in chemistry that has roots in ancient Egypt and Greece. It actually comes from the words, Greek words, stoichion, meaning elements, and metron, meaning measurement. And the word itself, stoichiometry, literally means measuring elements. And so it really just deals with the quantitative aspects or relationships between the products and reactants of chemical reactions. And so it's based on the law of conservation of mass, which basically says that matter can be neither created nor destroyed in chemical reactions. And so because we can balance these atoms, the mass on the reagent side and product side should be equal after the reaction. And so this allows for lots of things to be examined or calculated or quantified, dealing with things like efficiency of reactions, optimization or optimal amounts, yields, and so on. And we're going to examine some of those in today's video. Alright, so in this example, we're going to be tasked with sort of taking 17 grams of white phosphorus and reacting it with 15 grams of potassium metal at high heat to yield K3P7. And what we want to know is how much is theoretically possible in terms of that product. And so in order to unlock the potential of stoichiometry and to do this quantitative work, we're going to need to balance this chemical reaction. So again, if you're not sure how to go about doing that, that is covered in an additional video, so don't be alarmed. I'm just going to kind of show you how I do it. But to balance this reaction, we sort of need to look at our phosphorus on each side. We see that it's unbalanced. We need to look at our potassium, and we need to sort of find the least common multiple of those things to make it sort of work out. So that we have the same number of phosphorus atoms on the product side as we do the reactants as well as the potassium. And so I see 4 and 7, and so that seems to me like 28 would be the least common multiple of those things. And so if I put a 4 here, that gives me 28 phosphorus, so I need to do the sort of same thing here. I need to make 28 phosphorus on the reactant side, so I'm going to stick a 7 there. Last but not least, I have 4 times 3, which is 12 potassium atoms on the product side, so we need to stick a 12 for a coefficient on the reagent side, okay, to balance that reaction. Alright, so now that things are balanced, we can now do stoichiometry. And if we only had sort of one reagent amount, we could just sort of calculate how much we needed to add of the other reagent to do this a stoichiometric reactor, to use up all the reagents. But here we're given 2 amounts of the different reagents, so we can't just assume it's going to be stoichiometric. We need to find if there is a limiting reagent or not. And so the way that we go about doing that would be to take the masses of each of these reactants. So I'm just going to sort of list them here. And I'm going to convert those to the product, okay? And there's several ways to go about finding the limiting reactant, but because we're looking for the theoretical yield, okay, I'm going to go ahead and convert it all the way to grams of the product. You could take each one of these separately, convert them to moles of the product and get the same answer. You could also do what's called a ratio of reagents to find out which one would be limiting, or if there is a limiting reactant. So I'm just going to set it up the way that I generally do it. Again, there's many different styles and ways to do this, but it all involves sort of the same steps. So the first thing I'm going to do, and the first thing that you have to do in order to do stoichiometry, is you have to get into the land of moles, okay? So that's numbers of particles of things. This is a really big sort of amount of things. It's kind of like a dozen is 12. A mole is Avogadro's number of particles. And these coefficients, if we're doing lab scale work, they don't just mean 7 P4 molecules or 12 atoms of potassium. They mean 12 moles or 7 moles respectively of those things. Okay, so we're doing lab scale work, grams of stuff. So the first thing we got to do in order to use this balanced equation and do stoichiometry would be to get into the realm of moles. And so that's what I'm going to do. I'm just going to set up the units, the pathway, and I'm going to come back and I'm going to fill in the ratios, or the bridges as I like to call them, to complete this problem. All right, now that we have the equation balanced, what we need to do is get into the land of moles, right? The realm of moles, so we can use this balance equation and convert from anything in the equation to anything else we want. In this case, again, we're converting grams of each reagent separately to grams or moles of the desired product. So to start with, we're going to need the molar mass of the reagents, and so using a periodic table, we can obtain those. And so if you're rusty on that, you can actually check out another video that we're going to put out dealing with that topic. But just looking at the periodic table for potassium, the molar mass, I'm going to write them here, 39.098 grams per mole is the molar mass of potassium. And then for P4, we have 129 point, let's see, what did I have? 123, excuse me, 0.9 grams per mole as our molar masses. Okay, so now we can use those again, these molar masses as conversion factors between grams of potassium and moles of potassium. So here we just set up our brackets to have grams of potassium in the denominator, moles of potassium in the numerator. And so for every 1 mole, there are 39.098 grams of potassium. Write that there. There we go. Okay, and so for P4, same idea. For every 1 mole of P4, there's going to be 123.9 grams of P4. Okay. I'm going to rewrite this a little better. There we go. For every mole of K, there's that many grams of K. And so if we think about units canceling, grams of P4 will be gone. Now we're left with moles of P4 here. Grams of potassium's gone. We're left with moles of potassium. So now here's where the balanced chemical reaction comes in handy. We can use the mole ratios, which are essentially the correct ratios of the coefficients in our balanced chemical reaction, to convert from moles of potassium to moles of K3P7 and moles of P4 to moles of K3P7, and then we're going to examine which one's larger or smaller to determine the limiting reactant. Okay, so we're just going to set up our mole ratio, which I call the stoichiometric bridge, because this is the information that you're going to use, the conversion factor you're going to use that's provided by this balanced chemical reaction that will get you from one thing to another thing in that reaction. So here we see that for every, let's see, 12 moles of potassium, I'm going to produce 4 moles of K3P7. Okay, so here moles of potassium will be gone. I'm left with moles of the desired product. So I'm consuming that many moles of potassium to stoichiometrically react and yield 4 moles of the product. Here for P4, 7 moles of white phosphorus are used up, and that's going to again yield 4 moles of the desired K3P7. Okay, but we don't want to stop there, because again, we're doing lab work where we can't measure moles with the balance. We measure we measure mass with the balance. So let's go all the way to grams. And so by doing that, we also inadvertently will be arriving at the theoretical yield of the product. Okay, so we're going to find the limiting reactant and the theoretical yield sort of one swoop if we use this method. If you use some of the other methods, you may have to go a step or two further to get to the actual theoretical yield. So here, what we now need to do is determine the molar mass of K3P7. All right, so again, we need to find the molar mass of K3P7 so we can finish out converting these reagents to that desired product. And so if we sum up the atomic contributors of K3P7, we get a molar mass of 334.1 gram per mole. Okay. So now we can use that as our conversion factor to go from moles of K3P7 to grams just by doing what we've done for, say, dimensional analysis and canceling out units. So we'll set up our 2 brackets for each of the reagents separately. Okay, so I know that for every 1 mole of K3P7, I'm going to do them simultaneously, there's going to be 334.1 gram of K3P7. All right, so we've got our 2 separate reagents converted all the way to grams of the single product of interest. So all we got to do now is crunch it in our calculator. So I'm going to do this again separately, and I'm going to look at these values. I'm going to use that to determine the limiting reactant and the theoretical yield of this product in this particular reaction. So take our calculator, 15 divided by the molar mass of potassium times 4/12 times 334.1. And so what I get is 42.7 grams of K3P7 that could be formed if I use only 15 grams of potassium. And so from our P4, same idea, 17 divided by the molar mass of P4 times 4/7 times 334.1, and I get 26.2 grams of K3P7 allowed from that 17 grams of P4. So now looking at these two values, okay, I clearly see that there's a much smaller number of grams of K3P7 formed from the complete consumption of that 17 grams of white phosphorus. So what that tells me is that my limiting reactant, I'm going to use LR to describe that, is white phosphorus. So there's our limiting reagent or reactant. Okay, P4 is the reagent. A lot of students like to circle this and say it's the limiting reactant, but that's not true. This is a product. These are the reactants. We discovered that white phosphorus, or P4, was the limiting reactant in this reaction. And so that would make this value, because we've converted all the way to grams, okay, this would be, I'm going to label it TY for theoretical yield, okay, of the product. So if we ran this reaction and all went perfectly, this would be the maximum amount of K3P7 that we could form from these amounts of reagents. Okay, so just summarize what we did. We were doing stoichiometry. We're wanting to determine the amount of K3P7 that could be formed from the combination of 17 grams of P4 with 15 grams of potassium. Okay, so we took each reagent, each mass of reagent separately, converted to moles so that we could then use the balanced equation following the law of conservation of mass, doing quantitative work. So we could use that to get these mole ratios, or what I call the stoichiometric bridges, between each reagent and the product. From there, we just use a molar mass to get back out of the land of moles, back into a mass of the thing that we want. So here we see our two masses of product that were formed from each reagent, and we see here that one was much lower, indicating that this was our limiting reactant and that this amount of K3P7 would be the theoretical yield. All right, from our calculations, we found that the theoretical yield of K3P7 from these amounts of reagents, from 17 grams of P4, 15 grams of potassium, was 26.2 grams of K3P7. That was theoretically possible from that amount of reagents, right? So what we want to do now is determine the percent yield of this reaction if we actually isolated 20.5 grams of product. So we ran the reaction, we worked it up, isolated our product, and found the actual yield was 20.5 grams out of the 26.2 grams possible. Right? So the way that we calculate the percent yield is as follows. We're going to take this actual yield, we're going to divide it by the theoretical, and just multiply by 100 to convert it to a percentage. Okay, so if we do that, we have our 20.5 grams, so divide it by our 26.2 grams, multiply by 100%. And we see that our percent yield for this reaction is 78.2%. Pretty decent, okay? So that's how we will go through calculating the theoretical amount of a product of our interest that's possible from a certain amount of reagents. We had to find the limiting reactant to make sure that we didn't over or underestimate this. And then we can use that theoretical yield and the amount of stuff that we actually get or obtain after running the reaction in the lab to get to the percentage that we attained. Okay. All right. Thank you for watching.